Good morning, respected session chairs and fellow researchers. My name is Siam Rahman from the Military Institute of Science and Technology in Dhaka, Bangladesh. In this presentation, I will introduce our work, a dual pathway hybrid spatio-temporal graph neural network for regional electricity demand forecasting in Bangladesh power grid. This is a joint work with my co-author Tanvirul Tuhin and our supervisor MD Ahsan Kabir sir. Let me begin with the motivation. Electricity has one defining constraint: it cannot be stored at large scale. This means generation and demand must be balanced continuously in real time. Accurate demand forecasting is what makes the balance possible, and it directly affects the grid stability and operating cost. Now, why study Bangladesh in particular? Bangladesh is one of the most densely populated countries in the world, with rapid urbanization, growing industrial load, and a developing national grid. These factors make its regional demand highly volatile, and that makes it a demanding, realistic testbed for forecasting models. Here is the central limitations we address. Most deep learning forecasters, such as LSTM, GRU, bidirectional GRU, are purely temporal. They treat each region as an isolated time series. But a real power grid is not isolated. When demand rises in one region, that affects uh, through the transmission lines in neighboring regions. Purely temporal models are blind to these spatial interactions, and that blind spot is exactly what our work targets. Before the gaps, allow me 30 seconds of background so that the rest of the talk is clear. Bangladesh National Grid is operated by a utility called PCCB, Power Grid Company Bangladesh. For forecasting, the country is divided into 9 regional demand zones. These zones are linked by high voltage transmission lines, and crucially, that connectivity is very uneven. On central hub, the capital Dhaka connects to 6 other regions. Meanwhile, some peripheral regions at the country's edges connect to only one. Please keep this imbalance in mind because it drives the entire problem. With that, we identify three gaps here. First, temporal models ignore the spatial correlations carried by the physical network of a grid. Secondly, the obvious remedy. A standard graph convolutional network introduces a new problem called oversmoothing. Repeated neighbor aggregation gradually washes out the unique demand signature of the small peripheral regions, drowning them in the signal of the large central hub. Third, no graph-based spatio-temporal model had yet been applied to Bangladesh national grid using its true physical topology. Our contributions answers each gap in turn. We model the 9 regions as graph nodes using the real transmission topology. We design a dual pathway architecture that separates local temporal learning from global spatial aggregation. And this separation is what controls the oversmoothing. And we demonstrate complete outperformance over the existing baseline across the all 9 regions. This slide shows how we prepare the data. The pipeline has 6 steps. It begins with raw daily generation reports from the national utility and ends with a normalized graph structured input tensor. That tensor has 4 dimensions: batch size, a 10-day history window, the 9 regional nodes, and 13 features per node. Those 13 features combine demand history, weather data, fuel supply constraints, and calendar information such as holidays. In parallel, we construct the spatial graph itself. The nodes are the 9 regions, the edges are the physical high voltage lines or corridors connecting them, and we encode these as a simple binary adjacency matrix. On if two regions are physically connected, 0 otherwise. Finally, we add self-loops so that each region preserves its own information during the graph convolution. This is the core of our contribution, so I will go through it carefully. The model has two parallel branches. Branch A is the local temporal pathway. Here, we reshape the data so each region's timeline is processed independently through a two-layer bidirectional GRU because it reads each region in isolation. It learns that the region's own demand rhythm without interference from its neighbors. Branch B is global spatio-temporal pathway. Here, the data first passes through a graph convolutional block, which deliberately mixes each region's information with its physically connected neighbors. It then passes through its own bidirectional GRU block to capture how this grids wide relationship evolves over time. Now, here is the key idea, the region for two branches. By keeping the local history in a separate protected pathway, we prevent the dominant central hub Dhaka from overwhelming the small peripheral regions during the aggregation. In plain terms, the large capital region can no longer drown out the small edge regions. The two branches are then concatenated, and a fully connected block learns how much to weight local versus global information, adapting to where each region sits in the network. A brief summary of our experimental setup. The dataset spans November 2019 to December 2024, about 1,850 daily records across the 9 regions with 13 features each. The dataset is published in Data in Brief Journal. We use a chronological 80-20 split. This is important. It ensures the model never sees the future data during training and it reserves a full year of testing. The random seed is 42 for the reproducibility. The training we use the Adam optimizer with the mean squared error loss, a hidden dimension of 64, dropout of 0.2, best size 64. We apply early stopping and learning rate scheduler to ensure stable convergence. In short, the model looks back 10 days and predict the next day. Now the results. These plots show actual versus predicted day ahead demand for all 9 regions across the full test year. Please notice two things. First, the model captures both the broad seasonal envelope and the finer weekly cycles. Secondly, it does this across regions of vastly different scale, from capital in thousands of megawatts down to the smallest peripheral regions in low hundreds, like Sylhet and Borishal. The overall test MAP is 5.37%, equivalent to test accuracy 94.63%. And here's the most important observation. The largest improvements appears exactly where our theory predicted, at the small peripheral regions like Sylhet. This is the oversmoothing mitigation showing up directly in the results. This table gives the full regional breakdown for both training and test sets. The overall test error is 70.64 megawatts at 5.37% MAP. I would draw your attention. I would draw your attention to one detail. The gap between training and test MAP is small, 4.63 versus 5.37. This narrow gap tells us the model generalizes well and is not overfitting. Most regions stay below 5% error. The smaller peripheral regions remain the harder cases, as expected, given their smaller and more volatile loads. This slide is the direct head-to-head against the existing state-of-the-art bidirectional zero baseline on the same test set. The result is clean. Our model wins in every one of the 9 regions on both error metrics. And once again, the largest gains concentrate at the peripheral regions. This confirms our central claim, embedding the physical transmission topology while protecting local signals through the dual pathway is what delivers the improvement. We proposed a dual pathway hybrid ST-GNN grounded in the real physical transmission topology to our knowledge, the first graph-based demand forecasting model for a national grid. The dual pathway design mitigates oversmoothing, and this is validated by the largest accuracy gains appearing in the peripheral regions. Overall, we achieved 94.63% accuracy and complete outperformance over the baseline across all 9 regions. For future work, we plan to extend the model to hourly resolution forecasting and to explore asymmetric loss functions to better penalize the underestimation of the demand spikes. This concludes my presentation. I sincerely thank the session chairs and audience for your attention, and I welcome any questions during the Q&A session. Thank you.